We are going to discuss balancing of reciprocating masses. First of all, it is required to know how the unbalanced forces are created by reciprocating masses. For that, we have taken an example of single cylinder reciprocating engine in which the components are shown over here. This is crank, connecting rod, piston and cylinder, and the different forces which are going to act in the system are listed over here, where Fr is the force required to accelerate the reciprocating parts, Fi inertia forces due to reciprocating parts, Fn is the normal force, Fb is the bearing force. The acceleration of the reciprocating parts can be given by the equation AR is equal to omega square r cos theta plus cos 2 theta by n. Multiplying acceleration with the mass is going to give you the inertia force. So Fi, that is equal to m omega square r cos theta plus cos 2 theta by n. And this inertia force is going to be treated as the unbalanced force in the system. So this is represented as Fu. Fu, that is going to be m omega square r cos theta plus cos 2 theta by n. And just expanding this bracket, we are going to get m omega square r cos theta plus m omega square r cos 2 theta by n, in which the first term is treated as primary unbalanced force, which is going to be m omega square r cos theta, and the second term is treated as secondary unbalanced force. If we'll compare these two equations, we'll find something over here. Instead of cos theta, we are having cos 2 theta by n. As the value of theta is going to increase, the cos 2 theta value is going to decrease, as well as this term is also going to be divided by n, and that is going to be the ratio between length of connecting rod and crank radius, which is always going to be higher than 1. So the value of secondary unbalanced force compared to primary unbalanced force is going to be negligible for single cylinder or two cylinder engines. Primary unbalanced forces having larger value compared to secondary unbalanced forces, so it is desired to balance primary unbalanced forces. For that, we have to focus on the equation of primary unbalanced force, which is going to be m omega square r cos theta. So first of all, if we look at mathematically, what we are going to find that if mass m, which is going to rotate at omega speed, and it is located at some radius r, and at particular angle theta, we are going to get a horizontal component of this centrifugal force m omega square r, which is going to be m omega square r cos theta. So particularly we are trying to balance effect of m omega square r cos theta. For that, we require an horizontal force exactly acting in opposite direction with an equal amount. So for that, we can introduce a one rotating mass capital B over here, which is at radius small b, which is going to create b omega square b. It is going to rotate at the same speed, so it is going to create b omega square b, which is a centrifugal force, and we are going to get a horizontal component of this particular force, which is going to be b omega square b cos theta. So b omega square b cos theta, which is going to balance m omega square r cos theta. But the actual nature of the force created over here, which is going to be centrifugal, and it is created by a rotating mass capital B. So one vertical component will be also created over here, which is going to be b omega square b sin theta. So as we find that m omega square r cos theta can be balanced by b omega square b cos theta. At the same time, one component of a balancing mass that we have placed, which is going to create one centrifugal force, and the component of this particular force is going to be left out. So b omega square b sin theta will remain unbalanced. If we need to balance it, the iteration of adding a mass or removing the mass will go on. So the title given over here, which is partial balancing of unbalanced primary forces. So we are never going to get the complete balance of reciprocating masses. Some part is going to be always left out over there. So it is known as partial balancing of unbalanced primary forces. Detailed explanation is given over here, in which centrifugal force due to mass B, that is going to be omega square B, and we are comparing this horizontal component of this particular force B omega square B cos theta, that is equal to m omega square r cos theta, which is going to give you BB, that is equal to mr. But in fact it is not there, because one vertical component B omega square B sin theta, which is not been balanced. So we are not going to get the complete balance over here. So just we can say fraction of masses are going to be balanced. That fraction is taken as C. So fraction of reciprocating mass, C fraction of reciprocating mass is going to be balanced. So the equation can be rewritten as CMR is equal to BB. So from where we have started to balance the total mass M. Instead of that, we will just able to balance CM. Of course, the fraction C is always going to be less than 1. So the left out portion of unbalanced force, which is going to be m omega square r cos theta minus b omega square b cos theta. Ultimately, it is going to give you a result which is going to be 1 minus c m omega square r cos theta. Now this is the component which is going to act along the line of stroke. Okay friends, why? Because m omega square r cos theta, which is acting along the line of stroke, both these forces. So this is acting along the line of stroke, and in a vertical direction we are having b omega square b sin theta. So resultant unbalanced forces at any instant can be given by this equation m omega square r 1 minus c square cos square theta plus c square sin square theta. Now we are going to take a simple example of a single cylinder. For a single cylinder, just the data are given to you, like it is reciprocating at 240 rpm, stroke length is given 300 mm, mass of the reciprocating parts 50 kg, and all these data are given to you, and you are required to determine the balance mass required at a radius of 400 mm and the residual unbalanced forces when the crank has rotated 60 degree from top dead center. So first of all, we are going to determine balance mass required, right? So balance mass required is going to be BB, that is equal to MR. So M1 plus CM. Friends, we have to focus over here, because what we are going to do, we are going to balance complete revolving mass as well as fraction of reciprocating mass, right? So the fraction that is given as 2/3. If 2/3 of reciprocating parts are, and all the revolving parts are to be balanced, so 2/3 of 50 and 37, that is rotating mass. So in total you are going to balance this amount of mass multiply by radius, that is already given to us. So we can determine the balancing mass required, as well as residual unbalanced forces. Residual unbalanced forces is just a resultant of vertical as well as horizontal components. So it can be calculated by using this equation. So this is for single cylinder reciprocating engine. Now we are going to discuss the effect of primary unbalanced forces on locomotives. The locomotives usually have two cylinders with crank placed at right angles to each other in order to have uniformity in turning moment diagram. Locomotive can be classified as inside cylinder locomotives and outside cylinder locomotive. It is based on the location of cylinder with respect to driving wheels. So here you may find two cylinders has been placed inside two driving wheels, and here two cylinders are placed outside the driving wheels. Now cylinders are represented by crank number 1 and crank number 2. As you will find, the relative angle between crank number 1 and crank number 2 is 90 degree. It is same over here. One more classification is there for locomotive, is single or uncoupled locomotive or a coupled locomotive, in which if the front wheel and the rear wheel are connected by a coupling rod, in that case they are recognized as coupled locomotive, and if they are not going to be coupled, then it is going to be an uncoupled locomotive. The unbalanced force along the line of stroke is given by 1 minus c m omega square r cos theta. For the locomotive, we are having two cylinders, so two different forces of amount 1 minus c m omega square r cos theta and cos 90 plus theta will be generated over there. The resultant of both of these forces is known as variation of tractive forces. As per definition, if we are going to represent them, it is going to be Ft, which is resultant of unbalanced forces along the line of stroke. And we are going to get an equation 1 minus c m omega square r cos theta minus sin theta. Here we also require to determine the maximum or minimum value of variation of tractive force. For that, this term is going to be get differentiated and two angles can be determined, theta equal to 135 degree and 315 degree. At these two angles, the value of variation of tractive force is going to be maximum or minimum. So by placing this value in the equation, we are going to get plus or minus root 2 1 minus c m omega square r. So this is the equation that we have to remember for variation of tractive forces. The variation of tractive force is going to act along the line of stroke. The other effect that we are going to discuss over here, which is swaying couple. As you may observe in this figure, two cylinder lines are shown over here. This is for cylinder number 1, this is for cylinder number 2. Two forces 1 minus c m omega square r cos theta and cos 90 plus theta. So these two forces are going to form a couple with respect to a center line. So they will just try to sway the engine in anti-clockwise and clockwise direction, right? So they are going to form a couple at y axis. Now if we are going to take the neat couple over here, which can be represented as swaying couple, which is going to be force multiplied by distance and force multiplied by distance. One is going to be clockwise, other is going to be anti-clockwise. So at last we are going to get 1 minus c m omega square r a by 2 cos theta plus sin theta. Once again we are looking for the maximum value of swaying couple. For that we are going to differentiate this term, and after differentiating we are going to get angle theta equal to 45 degree or 225 degree. By placing these values in an equation, we are going to get the final result as plus or minus a by root 2 1 minus c m omega square r. This is known as swaying couple. So the variation of tractive forces and swaying couple, these are the two effects which we are going to get due to unbalanced forces acting along the line of stroke. But as we know, to balance the reciprocating masses, we have placed a one additional mass, which is capital B, and the vertical component of the force created by mass B is b omega square by b sin theta, which is still unbalanced. The maximum value of this unbalanced force is going to be b omega square b, as sin theta is going to be 1 or minus 1. So we may have maximum magnitude b omega square b, which is known as hammer blow. But as we know, when theta is going to be 90, it is going to be plus b omega square b, and if it is going to be 270, it is going to be minus b omega square b. Now the net pressure on the wheel and the rail, if P is going to be the dead weight of the engine, so the net pressure can be written as P plus or minus b omega square b. The maximum value of hammer blow can be equal to B, so it can be written as P is equal to b omega square b, which is much more important as it is going to decide the permissible value of the angular speed. If the value of omega is going to increase by an extent where P is less than b omega square b, in that case there are chances that the engine can be derailed. Whenever b omega square b having a higher value, but if it is going to act in a downward direction, at that time they are going to apply the pressure on the rails. But when b omega square b having a higher value and it is going to act in an upward direction, and if it is greater than P, in that case there are chances of derailing. So the speed of engine is much more depending on the value of hammer blow. Here we are going to take an example of inside cylinder locomotive, in which cylinder center lines are 0.7 meter apart and the stroke length is 0.6 meter. The rotating mass is per cylinder is 150 kg and reciprocating mass per cylinder is 180 kg. The wheel center lines are 1.5 meter apart. By using these dimensions, first of all we are going to locate the different planes. Two planes for wheel on extreme left and on extreme right, and two cylinder at plane B and plane C. The important thing is that the whole of the rotating and 2/3 of reciprocating masses are to be balanced by masses placed at a radius of 0.6. So first thing that we have to focus on is whole of the rotating, that means 150 kg has to be balanced. Along with that, 2/3 of reciprocating mass, that means 2/3 of 180 kg need to be balanced. Now this mass is going to be 150 plus 2/3 into 180, which is going to be 270 kg. So in plane B and plane C, 270 kg mass is going to be placed and it is going to be balanced. One important thing is that the balancing mass will be always placed in the plane of wheels, and where it is going to be located is given as a radius of 0.6 meter. Now here we are going to determine the magnitude and direction of the balancing masses. Along with that, we are also going to determine fluctuation in rail pressure, which is known as hammer blow, variation of tractive effort, and magnitude of swing couple. There are two methods of solving such equations. One is analytical and another is graphical. Whichever method we are going to follow, the first thing that we need to do is to represent the planes as shown in this figure. Then we have to calculate the masses to be located in the planes of cylinders, where already we have gone through this calculation, like whole of the rotating mass and 2/3 of reciprocating masses, they are going to be 270 kg. So 270 kg is going to be located in plane B and plane C. First of all, we are going to discuss analytical solution. For analytical solution, we can prepare a table like this, in which we are going to represent all the planes in the first column, where the sequence of the planes are going to be same as they are going to be placed in this diagram. So A, B, C, D are going to be placed over there. One of the plane has to be selected as a reference plane. There is a simple criteria of selecting a reference plane. The general criteria of selecting a reference plane is to select a plane on an extreme left. And one more thing is there, if we are having few unknown values like mass and angle in that particular plane, then it has to be preferred as a reference plane. It is not mandatory to select a reference plane on extreme left only. We can select also on a right hand side, like here plane D can also be selected as a reference plane, but whenever the calculation part is going to take place, all the distances from the reference plane will be negative over there. Just to avoid that negative sign, we are just preferring plane A as a reference plane. So in a first column we are going to represent all the planes. In the second one we are going to represent the masses, where in plane A and plane D we are having unknown masses. 270 kg, 270 kg, that is the mass which we are going to calculate by using this equation, where 150 is the rotating mass and 2/3 of reciprocating mass. So 270 kg has to be placed in plane B and C, which are the plane of cylinders. Here the radius of rotation. In the next column we are having angles. Angle in plane A and plane D are unknown for us, so that is theta A and theta D. Here the distance is L, which will be measured from reference plane. So from plane A to A the distance is going to be 0. From A to B it is going to be 0.4, A to C that is 1.1, and A to D that is 1.5. Now these next two columns are representing the component of the centrifugal force created by the respective masses. So here it is just for explanation, it is written as mr omega square cos theta, that is a horizontal component of a centrifugal force mr omega square. For a mathematical simplification, we are just avoiding omega square over here. So it has been written mr omega square cos theta by omega square. Otherwise, in each and every calculation, we have to repeat the value of omega square. So this entire term, which is a horizontal component of centrifugal force is represented by mr cos theta. Similarly, for a vertical component, we are going to use mr sin theta. Now in next two columns, we are having couples. So couples will be force multiplied by distance. So the force is going to be mr omega square cos theta, which is a horizontal component, multiplied by L. And similarly, we are avoiding the calculation of omega square. So for mathematical simplification, everywhere we have avoided omega square. So MRL cos theta, which is going to represent the horizontal component of the couple created by the respective masses. Similarly, the vertical component can be represented by MRL sin theta. For further calculation, we are going to focus on the last two columns, in which we are going to get this term as a 0, as the value of LA is going to be 0. So similarly, we are going to get 0 over here. So in this column, we are going to get three numerical values, 0, 32, 0. Here also we are going to get 0, 0, 89. And this is going to be an entirely unknown term. But within that, we are going to find out that RD, that is radius of rotation, which is given as 0.6, as well as LD, which is going to be 1.5. So we are having two known values, and MD and theta d are going to be unknown. Similarly, we are going to find MD and sin theta d over here, in which theta d is unknown and MD is unknown for us. Now the concept is of dynamic balancing is there, in which the net couple acting on a system must be 0. So sigma C is equal to 0. For that, sigma MRL cos theta has to be 0 and sigma MRL sin theta has to be 0. So summation of all these four terms has to be 0, which is going to give you the result like this. Now by taking the ratio of these two terms, we are going to get tan theta d, and from which we can derive the value of theta d as 250 degree. By placing the value of theta d in any of this equation, we are going to get the mass value, that is md, which is equal to 105 kg. Angle theta d and md can be used in the column of forces, where we are having a term md rd cos theta d, md rd sin theta d, which can be calculated by using these two values. So this entire term will have some numerical value. Fine. So in this column, we are going to apply the concept of static balancing, where sigma f is equal to 0. For that, sigma mr cos theta has to be 0 and sigma mr sin theta has to be 0. So by using this relationship, we are going to get ma cos theta a. Already we are knowing the value of ra and ra over here. So it is going to give you ma cos theta a, ma sin theta a. And by taking this ratio, we are going to get theta as 200 degree, and by placing the value of theta a over here, we are going to get the mass value. Fine. So in this way, we will able to determine the location as well as the value of the masses. So this is how we are going to deal with the analytical solution. One thing that we have to take care of, because while we are going to calculate these angles, using any of the calculator, you are going to get the value of theta, which is always going to be less than 90 degree. But first thing that we have to do, we have to decide the quadrant. Friends, if you focus over here, we are going to get ma cos theta a, that is equal to minus ma sin theta a, that is equal to minus. See, ma is never going to be negative. So the sign is controlled by cos theta a and sin theta a. If cos and sin both are negative, that means we are in third quadrant. Same thing over here, cos theta d and sin theta d both having negative values. So it is in third quadrant. So the angle we are going to get, which is going to be in third quadrant, because through direct calculation using a calculator, you are never going to get theta a equal to 200 degree or theta d that is equal to 250 degree. The same problem can be solved by graphical method, in which first of all we have to prepare a table like this, in which the first column is representing the different planes A, B, C, D, as well as the respective masses, radius of rotation, centrifugal forces, distance from reference plane, and couple. Here we are not going to deal with the angles. So instead of taking horizontal or vertical component of centrifugal forces and couple, simply we are representing them with MR and MRL. Fine. So This is how we are going to prepare a table. After preparing a table, we need to represent the masses with their angular positions. Right now, the masses in plane B and C are known to us, as well as the angular position of these masses are also known to us. So it is up to you that you can select the position of one of the mass. Say right now we are going to select the mass in plane B at 0 degree. So with respect to that, the mass in plane C will be placed exactly at 90 degree to mass B. Fine. These are the two masses MA and MD for which the value as well as the angular position are unknown for us. Fine. So to determine this angular position and mass values, first of all we have to focus on the couple column where we are going to deal with different four values. One of them is going to be 0. So it is going to form a couple polygon. As we know, there will be three values, so the couple polygon is going to be a triangle. First of all, we are going to take 32.4, which is a couple created by mass placed in plane B, and 89.1, which is going to be a couple created by mass placed in plane C. So here we are going to represent 32.4 over here and 89.1 in a vertical direction, and the closing side is going to be 0.9 MD. Here we need to use a proper scale. By using a scale, we are going to get the value of MD. To determine the angle, one line parallel to this 0.9 MD vector has to be drawn on this space diagram, which is going to represent the angular position of mass MD. Now, the value of MD which has been derived through this calculation can be used in the column of centrifugal forces, where we are going to use the value of MD over here. So we will have three known terms over here and one unknown term. So the polygon which we are going to get for centrifugal force, that is force polygon having four sides, right, in which the known values 81 can be represented over here, 81 that can be represented over here, and 0.6 MD which will be represented over here, which is parallel to this one. Fine. So the closing side is going to be 0.6 MA. Once again we are going to use a proper scale, and by using the scale we are going to get the value of MA, that is equal to 105 kg, and theta A. Theta A can be determined by drawing a parallel line to this one. So this vector we are going to draw a parallel line which is going to represent the angular position of mass MA, which is going to be 200 degree. To determine fluctuation in rail pressure, first of all we have to focus on this equation, which is B omega square B, where capital B is representing the balancing mass required for reciprocating masses only. The balancing mass we have determined so far is 105 kg, which is actually including the balancing mass required for rotating as well as reciprocating. So 105 kg has to be divided in different two sections, one section or one segment which is going to be used for rotating masses and other is going to be used for reciprocating masses. So by simple ratio method we can have division of 105 kg in different two sections, that is 58.3 kg, which is going to be utilized for rotating masses, and 46.6 kg is going to be reciprocating masses. So this is going to represent capital B. Here the general mistake has been observed that straight away we are using 105 kg for capital B, which is not true. So by using this value we can determine the value of fluctuation in rail pressure, which is also known as hammer below. Now for variation of tractive effort, the equation is already been discussed previously, where one more mistake that we are commencing over here, instead of M2 straight away we are using value of 270 kg that we have used in that table. Friends, M2 is actually representing the total reciprocating mass, which is 180 kg. It is not actually fraction of that particular mass like 2/3 of 180 or 2/3 of 270. It is not like this. It is purely reciprocating mass which we are going to use in this equation. C is the fraction that we are going to use, which is 2 by 3, already given to us. Omega can be calculated from the speed given to us. And R is going to be the crank radius. See, we are having one more radius over here where the balancing masses are going to rotate. Friends, we are not going to use that radius over here. This R is crank radius. Fine. So by using all these terms given over here, we can calculate the variation of tractive effort. Similarly, we can determine the value of swaying couple, where A is going to be the distance between the planes of cylinders, right? And once again we are going to use value of M2. M2 is going to be the reciprocating masses. We are going to see one more numerical in which there are 3 cylinders. The data are given like this. The 3 cranks of 3-cylinder locomotives are all on the same axle and are set at 120 degree. The pitch of cylinder is 1 meter and the stroke is given as 0.6. Reciprocating masses are 300 kg for inside cylinder and 260 kg for each outside cylinders. The planes of rotation of balancing mass are 0.8 meter from inside cranks. So by using these dimensions given over here, first of all we have to look at all the planes, in which plane A, plane B and plane C, which are going to represent the planes of cylinders, and 1 dash and 2, these are the 2 planes which we are going to use to represent the plane of balanced masses, right? So the distance is given over here. The pitch of the cylinder is given as 1 meter, so A, B, C are going to be located at 1 meter, and at the same time the plane of balanced mass is going to be placed at 0.8 meter from the center plane, right? Now the masses are different for outside cylinder and inside cylinder. For outside cylinder it is 260 kg and for inside cylinder it is going to be 300 kg. So for mass to be placed in plane B, we have to go through the percentage of reciprocating parts are to be balanced. So 40% of 300 kg, that is going to be 120 kg. So 120 kg is to be placed in plane B. Similarly, 40% of 260 kg, that is going to be 104 kg. So 104 kg is to be placed in plane A and plane C. First of all, we are going to see analytical solution, in which the table has to be prepared in a similar way we have prepared in the previous example, where the first column is representing the different planes, masses, radius, angle, length and so on. Here the plane 1 has to be selected as a reference plane, as the value of mass and angles are unknown for us in this particular plane. Fine. The other mass values are known for us. Similarly, the radius of rotation are known for us, and the angle that we are going to take, there is always a choice for you that you can select one of the mass at a particular location. So right now we are going to select the mass in plane A at 0 degrees. So the mass in plane B can be placed at 120 degree and NC can be represented at 240 degree. Further, we are going to focus on the last 2 columns to get the value of unknown masses and angles. So sigma MRL cos theta and sigma MRL sin theta both are equal to 0. By using this relationship, we can get the value of theta 2 and B2, mass B2 likewise. By using these 2 values in the earlier 2 columns, MR cos theta, MR sin theta, where we are going to get sigma MR cos theta is equal to 0, sigma MR sin theta is equal to 0. So by using both this relationship, we are going to get the value of theta 1 and B1. To solve the same numerical using graphical method, first of all we have to prepare a table like this, in which the first column, which is going to represent the planes, then mass, radius of rotation, centrifugal forces, distance from plane and couple. The first thing that we need to do is to represent the known mass with their angular position, right? So mass A, B and C, they are represented at the phase of 120 degree to each other. Fine. Then we have to focus on the last column, which is representing the couple. As we know, one of the value is 0 over here. So the couple polygon which is going to be formed will have 4 sides, and one of the side will be unknown to us. Fine, so we'll start with minus 6.24 over here, which will be drawn in the negative direction, then 28.8, which is going to be parallel to B, then 56.16, which is parallel to C, right? And the closing side is going to give you the value of 0.96 B2. So by using a proper scale, we can have the value of B2 that is equal to 57.5 kg. The same line will be drawn over here, which is parallel to this one, which is representing the angular position for mass B2 over here. We have to take a little care over here as far as direction of vectors are concerned, because this vector is towards the first quadrant. So while we are going to draw a parallel line to this vector, which will be drawn in the first coordinate side. So the location of mass B2 will be in first quadrant, right? So by measuring that angle, we are going to get theta 2, that is equal to 24 degree, and by using a scale, we are going to get B2, that is equal to 57.5 kg, right? So this B2 value can be further replaced in this column where 0.6 B2 is there. So we'll have 4 known terms and 1 unknown terms. These centrifugal forces are to be represented by force polygon, right? In which first of all we are going to represent 31.2, which is towards mass A, then the force created by 0.6 B2. Friends, just we have to focus on one more thing, that after we are going to represent the centrifugal force created by mass A, that is 31.2, then onwards we are having mass B2 over there. So whatever sequence we are having over here, but after placing one of the mass, we are going to follow the sequence which is represented graphically over here. So after mass A, we are going to represent the force created by mass B2, right? So it is going to be 0.6 B2. Then the force created by mass B, which is going to be 36. Then 31.2. Of course, 0.6 B2 is unknown for you, so it is always going to be closing side, right? So the closing side is going to represent 0.6 B1, and by using a scale, we can have the value of B1. As well as we are going to represent a line over here which is parallel to this vector, which is representing or determining the position of mass B1, which is in third quadrant. Till now, we have gone through the example of uncoupled locomotive. Now we are going to see balancing of coupled locomotive. In coupled locomotive, the driving wheel and trailing wheels are connected by a coupling rod, and these coupling rods are facilitated by a coupling rod cranks. The coupling rod cranks are placed diametrically opposite to the adjacent main cranks. So if we will focus on this diagram, we are going to find different 6 planes, in which the 2 planes are for cylinder 1 and cylinder 2, 2 are for wheel 1 and wheel 2, and another 2 planes are there, which is coupling rod 1 and coupling rod 2. These 2 planes were not there in uncoupled locomotive. Now, about the angular position of the coupling rod crank. If the cylinder 1 having a crank and its angle is 0 degree, in that case the angle for coupling rod crank is going to be 180 degree. It is going to be diametrically opposite to the adjacent main crank. So if angle is 0 over here, here we are going to get 180 degree. Similarly, the crank for cylinder 2 will be at 90 degree. So the coupling rod crank in plane F will be at 270 degree. So this is how the coupling rod cranks and the main cranks are going to be positioned. Here we are going to take an example in which data are given like this. First of all, we have to see the word coupled wheels. Fine, it is going to differentiate the earlier example of uncoupled locomotive. The stroke length is 650, mass of reciprocating parts per cylinder is given, mass of revolving parts
mass of each coupling rod, because this is going to be additional data that we are going to get for the coupled locomotive, where the mass of each coupling rod is given. Radius of center of coupling rod pin, that is 250 mm, distance between cylinders, distance between wheels, distance between coupling rods. Right, so these are the distances given to us. One more thing that we have to focus on, what is the fraction that we are going to use. Here 3/4 of the reciprocating masses are to be balanced along with the whole of the revolving masses. The balanced mass for reciprocating mass is to be divided equally between the driving wheels and the coupled wheels. Now friends, this is most important thing that we have to focus on, like the balanced mass for reciprocating masses is to be divided equally between the driving wheels and coupled wheels. That means whatever amount of reciprocating masses we are going to balance has to be divided in two different parts, or say two equal parts. One has to be placed in a driving wheel, other has to be placed in the rear wheel. So how we are going to do this, that we will observe over here. First of all, we will follow the analytical solution in which the total reciprocating mass is 240 kg. Fraction C is 3/4. So 3/4 of 240 kg is total of 180 kg reciprocating masses which we are going to balance. But as we know, this is total reciprocating mass. We have to divide in equal parts. So 180 will be divided in equal two parts. 90 kg will be in a leading wheel and 90 kg will be in a trailing wheel. So on one side we are going to balance 90 kg of reciprocating masses, and 200 kg is going to be the revolving mass. So 200 kg plus 90 kg, that is 290 kg. So in a leading wheel we are going to balance 290 kg of total mass, as well as we are having a coupling rod. The total mass of coupling rod is 250 kg. As we know, it is not going to be a purely rotating element, but still one consideration that we have to make over here, in which we are going to consider it as a rotating element, and that 250 kg will be divided in two sections. Half of the section will be considered with leading wheel and half of the section will be considered with trailing wheel. So in a plane A and F, which are representing the coupling rod plane, where we are going to consider 125 kg in leading wheel and 125 kg in trailing wheel. So by using all this value, we are going to prepare the table in a similar manner. The table can be prepared in a similar way what we have done so far with uncoupled locomotive. So here we are going to represent all the planes, all the masses, radius, angle, length, mr cos theta, mr sin theta, mrl cos theta, mrl sin theta. This you have to focus on this angle. As we know, one of the mass is to be represented at 0 degree, other is going to be at 90 degree. So corresponding coupling rod crank will be at 180 degree to the adjacent crank. So here it is going to be 90 degrees, so we will have 270 degree over here, and one angle is 0, so corresponding angle of coupling rod crank is going to be at 180 degree. The other procedure will remain same, as we are going to take B as a reference plane, and from B we are going to measure the distances. The couple that we are going to get for mass P or plane B is going to be 0, and sigma mrl cos theta, sigma mrl sin theta both are equal to 0. By comparing these values, we are going to get the value for the angle as well as masses. So by using this value, once again we can determine the value of theta B and mb. So the angle and masses that we got over here, these are for leading wheels. Right, similar procedure we have to follow for the trailing wheels. In trailing wheel, we are going to prepare a similar table in which first of all we are going to represent the planes. We have to focus on the value of masses. For the plane A, which is representing the coupling rod plane, the total mass of coupling rod was 250 kg. It has been divided in two sections. Half of the section has been considered with the leading wheel and half is going to be with trailing wheel. So 125 kg, 125 kg on both the plane A and F. Now in the plane of cylinders, C and D, we do not have any rotating parts over here. We are simply going to take the half of the part which is to be balanced. Like we have to balance 180 kg of reciprocating mass. So out of 180, 90 kg has been considered with leading wheel and 90 with the trailing wheel. So 90 kg of reciprocating masses has been placed over here. All other values will be written in a similar manner, and further the calculation will be done in the same way, and we are going to get the value of angle theta E, ME, theta B, MB. So these are the value of masses that we are going to place in the trailing wheel, right? Now we are going to determine the value of hammer blow. To determine the value of hammer blow, we can neglect these two planes, plane A and plane F, right? So we are going to deal with four planes, that is B, C, D, E. Double dash has been used for hammer blow only, right? So we are going to get value of MB and ME over here. MB and ME are going to represent the mass required to balance the reciprocating parts only. So right now in the front wheel or a leading wheel, we are going to get 90 kg of reciprocating mass on each cylinder to be balanced. In fact, they are more than that, but already we have taken a fraction of 3/4 of total reciprocating part, which is to be balanced. So by using all this calculation and a similar procedure that we have done so far, we are going to get the value of ME and MB, that is equal to 33 kg. So this is going to be the value of capital B that we are using to determine the hammer blow. So hammer blow is given by plus or minus B omega square B, where capital B is the mass required to balance the reciprocating parts only, and small b is going to be the radius of rotation omega, which can be derived from the value of velocity given to us. So by using all this value, we can determine the value of hammer blow.